Hello, and welcome to Introduction to Propositional Logic. We are going to be shifting gears quite a bit and exploring a different kind of logic, beginning now until the end of the semester. You will see a lot of parallels. There will be a lot of things that feel similar, but there will also be a lot of things that feel different. I think one of the things that is important to understand is that logical thinking is a language. And as a language, there are different ways to kind of represent the message. And these different ways of representing the message can sometimes change what that message is. So for any of you, for example, who are bilingual, who if you know how to speak more than one language, you might have noticed this, that saying something in one language and then trying to translate it directly into another language often will cause that sentence to lose some of the original meaning or take on meaning of its own. And that's because like that thing that you are trying to communicate, the truth or whatever it is, gets structured differently, gets sort of represented in different ways, depending upon the vocabulary, the context, and the grammatical structure of these different languages. And when you take something like English or Spanish or Chinese, these natural languages, these ordinary languages, these languages that have grown through in historical contexts, they will represent language often, or they will represent their messages often because of how language was used in the recent or distant past, meaning that even words that sound the same or have similar origins are going to take on different meanings. These languages that we're using in logic, we talked about this earlier in the semester, they are called formal languages. These languages are invented for the sake of making things clear. But in order to do so, decisions need to be made about what elements of the message must be made more clear than others. It is like designing a machine of truth calculation. And then in that truth calculation, we have to decide which things we're going to turn into the gears and the pulleys, and which things we are going to sort of leave to the side and not deal with. Categorical logic, the one that we have been studying, is going to represent truth, is going to represent logical relationships in one way, primarily through the construction of a categorical statement and the interlocking of the terms within those statements. Meanwhile, propositional logic is called propositional logic because its sort of simple element is the proposition. A proposition is something similar to a sentence, but it's not quite the same thing. A proposition is something that asserts a truth. And so what we're going to see is that in propositional logic, the relationships that we can build between one statement and another are much more complex than what we could have done in categorical logic. However, we lose something as well, and what we lose is the ability for individual statements to connect to one another because of what's inside of them. In other words, in categorical logic, we had something called a middle term. Remember, the middle term is that term which connects both premises in an argument that allows for a conclusion to come out of that. We can see what conclusion follows from those premises. Propositional logic doesn't have that feature, so we would represent the propositions with simple statements, and we wouldn't know how those statements are related until that information was provided to us in a different way. So I'm not sure how much that made sense, but hopefully that will crystallize as we look at some examples, not just today, but over the course of the next few weeks and even the next couple of months. In your book, propositional logic is going to cover chapters 10 through 22. And it is our goal to get to about chapter 21 by the end of the semester. In this week, we're going to be looking specifically at chapters 10 and 11, potentially 12. This talk will talk, or this video will talk primarily about chapter 10. This is the first video. Okay. Next, for just a little bit of history here. I mentioned before that categorical logic was an invention of Aristotle. It is therefore an invention of ancient Greek culture. For better or worse, and there's lots of interesting discussions we had around this, many of the philosophies, many of the theories that were born out of Greece have evolved, emerged into a very influential force, and now it has influenced many of the ways that we still deal with this stuff in how our language works 2,200 years later, in how our laws are structured, in how mathematics works, in how science is discussed, and in how computers work. This is not to say that this language, this categorical logic, was the only one or the best one. It's simply the one that happened to, I mean, that's an interesting discussion in itself, but there were other systems of logic in the world. And what it does mean, however, is that it's a language that we have to contend with now, either in its criticism or in its use. But along with Aristotle, so Aristotle back in the ancient Greek world, just a little bit of more context about this. You may know, if you've taken other philosophy classes or you've studied philosophy before, back in the 5th century BC, these are like the 400s BC. This is the time of the high democracy of Athens. This is when sort of, whenever you hear the democracy of Athens or the historical origin of democracy discussed, it's usually talking about this time in Athens. And one of the things about Athens is that although it had a democracy, every citizen could vote, which was very unusual at the time. Not everyone was a citizen. In fact, only a very small minority of the inhabitants of Athens were counted as citizens. And Athens was itself the sort of seat of a rapidly escalating empire. It's one of the things that often gets left to the side, is that in order for Athens to maintain its cultural and political influence and stability, it needed to sort of pull from the culture and the wealth of all sorts of other Greek city-states and non-Greek cities around the Mediterranean and from further beyond. Athens was a fairly cosmopolitan city at the time, where lots of different ideas were coming in from around that corner of the world. And a lot of these ideas, you know, when you have a lot of thinkers in one place discussing ideas, it attracts more thinkers. You know, this is like what the concept of the university is. Thinking well is aided by other people thinking and presenting ideas, criticizing other ideas, seeing their ideas grow. Aristotle was not a native-born Athenian. He was attracted to Athens largely because Plato had built a school there. And Plato, it was teaching philosophy, discussing philosophy, and lots of people from the Mediterranean and beyond, even some Persians and Arabs and Egyptians and other people from North Africa and Spain and Italy were coming to Athens to hear about, to explore their own philosophies, their mathematics and art and so forth. And so like this was a sort of hotbed. There was no historical, well-grounded theory of mathematics yet. There was no well-grounded theory of logic yet. These were all things that people were figuring out for the first time in their history. To do anything beyond counting and adding and subtracting, this is a fairly new thing. I mean, this is also the time, you know, roughly around the same time that astronomy was begun as a science, as an intersection of mathematics and science and geometry. This was when books were being written about the different kinds of animals in the world. This was the time when people were writing about what makes a play, what makes a story, what are the elements of a story. Like so many of these ideas, there was an explosion of ideas coming out of this place. And Aristotle comes up with this one idea for what is logic, for what is a sort of formalized way of verifying good thought. But it wasn't the only one. And there was another group of philosophers called the Stoics, who came up with another kind of logic. The Stoics are understood now as being the sort of inventor of propositional logic, what we call today propositional logic. You can read more about this in our book at the beginning of chapter 10 or elsewhere. But you may have heard of the Stoics before. And in fact, to call someone Stoic carries meaning even if you don't know what a Stoic is. And oddly, the word Stoic comes from the word stoa, which simply means a garden or a gardened area. And it gets its name because these group of thinkers, this small group of thinkers, was just one group of many in Athens, and they always hung out by the garden, taking walks and talking about things, a certain theory of what it means to be human. And this gave birth also to a kind of logic. So just as an aside, we often use the phrase to be stoic as something like when we say someone is stoic, it means that they seem to lack emotion or seem to be able to transcend their emotion. And the Stoics believed that genuine free will required that we use logic to make our decisions, and it would allow us to transcend our emotions. We want to separate our will and the choices we make with our body and the things that happen to us. So there's this notion that we are two separate things. Our mind, our reason, our choice is what we essentially are. Meanwhile, our body, our emotions, is what we inhabit. It's like our vehicle that we ride around in. And the Stoics advocated that the key to sort of happiness and enlightenment is to understand that what I am responsible for is only my mind. And the chief source of misery is when we believe that the things that happen to us are actually also a part of us. And so like if I feel sadness and I don't understand, and I did not choose the sadness, it causes me to be sad, and it causes me to be further more sad. And that the sort of way to escape this is to basically understand, you know what? That thing that made me sad today, that's not me. I did not choose that. And what I can only be responsible for the things that I choose, and to have that strong separation there. Anyway, if you're interested, let me know. We can go down that whole rabbit hole further. Moving on. So I mentioned this before, whereas categorical logic dealt with the relationship between the subject and predicate within a statement. So remember that. That in categorical logic, we dealt with the subject term, the predicate term, the minor, major, and middle term. So we're looking at the insides of a statement in categorical logic. Propositional logic goes in the opposite direction. It looks at the statement as a whole. And we are no longer going to worry about the subject and the predicate for the time being. The limitation of categorical logic is that it only allows us to deal with two premises and one conclusion, always in basically the same manner, by connecting that middle term together. And it's just setting those two statements side by side. Here's one statement, here's a second statement. And then because of that middle term, it allows us to draw together the minor and the major term. So functionally, if you think about it, in a categorical argument, in a categorical syllogism, we aren't given any relationship between premise 1 and premise 2. Or maybe a better way to say it is that the only relationship we are allowed is going to be represented with the term and. Premise 1 is true and premise 2 is true. But there are many other different types of operators as alternatives to the operator and. We're going to be dealing with what does it mean if we were to say premise 1 is true and premise 2 is false? Or either premise 1 is true or premise 2 is true, and we don't know which one. Categorical logic had no mechanism for that. Propositional logic, Stoic logic, does. This is going to allow for much greater complexity in the argument, going on to point 3 here. It's going to allow us to build arguments that have dozens of different parts to it. Not that we're going to get to that level in this class, but trust me, by the time we get to the arguments we're going to get to, you're going to be like, okay, that was good, Professor Swanson. That was good, complex enough for me. Some of you might let me know when we get to the end of the semester if you are craving more. There's always more to be had. But these arguments will allow us to go far beyond the two-premise structure that we saw with categorical syllogisms. We will be able, and now I'm not just talking about stacking multiple categorical syllogisms like we did with Sorites. I'm talking about having a single interconnected argument that cannot be reduced any further with 8, 12, 15, whatever premises. This is also a more direct predecessor to modern computer programs. And in fact, if any of you have had a taste of computer programming, or in mathematics, something called discrete mathematics, a lot of this is going to feel familiar to you. And in a way, a computer program is an argument, where every line of that argument is saying, if this is true, then do this. And it'll bring you to a different line in that code. Okay. Now, here's an important page. And again, I always encourage you, if you really want to understand this, and if you want to do well on the quizzes to come, this is the area where you want to be reviewing it, reading along with the book, and certainly by the end of this week, doing some exercises on your own. And I've got a few exercises to help us understand the basic concepts here. Okay, first, each statement will be abbreviated with a single letter. We're not going to necessarily start out with this at the beginning. In our book, they don't do the symbolizations until, I think, chapter 13 or 14. But I think it's useful to start talking about it earlier rather than waiting for the book to let it kick in. The book will gradually bring you in one way, but I sometimes think it's nice to sort of as we say, scaffold some of these later concepts in so that it makes a little bit more sense when we get there. But each statement is going to will be abbreviated by a single letter. So you think about a statement like, the car is blue. If I were to ask you to translate that into a categorical statement, you might have said, some cars are blue vehicles. Here we can just symbolize that whole thing as the letter C. And the letter C will then symbolize that whole thing, the car is blue. Meanwhile, R might be something like the car is red or something like that. We are also going to talk about truth values. Now, we've talked about truth values a little bit before. Each statement will have a truth value, either true or false. If a statement is not true, it is false. If a statement is not false, then it is true. Seems pretty simple, right? But trust me, this is one thing where I do get questions a lot as we go on. I'm never quite sure why. This never really clicks. But if I were to say something like, let's try something simple. Springfield is the capital of Illinois, right? Take that sentence, that statement, that proposition. Springfield is the capital of Illinois. That whole proposition will then be able to be translated into a single letter. Let's say I for Illinois. It doesn't really have to stand for anything. It's sort of arbitrary, but it can be useful to have a letter that's in the sentence. Springfield is the capital of Illinois, that's I. What is the truth value for that statement? And because you know, presumably, that the capital of Illinois is in fact Springfield, you would be able to say the truth value for that is true. Meanwhile, so you take another sentence like Chicago is the capital of Illinois. What is the truth value of that? And of course, the answer to that would be it is false. Now, sometimes you may not know what the truth value of a statement is. If I were to say, maybe some of you remember this, but if I were to say something like Seattle is the capital of Washington State, what is the truth value for that? Now, if you just know, then you know. But you might say, well, I don't know what it is. But you do know that it is either a true statement or a false statement. It's like one of those things. So it's important to understand that propositional logic is going to be another version of logic that is going to deal with truth in a binary way. That's not to say that all truths should be dealt with in a binary way. And this might be understood as a limitation for propositional logic. But certainly for a lot of things, what we might just call facts, simple facts, we can understand that it is, at the end of the day, even if we don't know what the capital of Washington is at the get-go, we certainly can understand that that statement is either true or false, because we know, based on the fact that Washington is a state, and I'm not talking about DC, I'm talking about the state north of Oregon and west of Idaho. We know that Washington has a capital. It's just a matter of, is it Seattle or not? As it so happens, that is not the capital of Washington. So to say that Seattle is the capital of Washington, that would be a statement with a false truth value. So it's always going to be true or false. Sometimes it might be undetermined. Sometimes it might be an unknown. But that doesn't mean that it's like somewhere in the middle. Okay. Next up. Okay, we already talked about that. The car is blue. So often we're just going to see a single letter by itself, C. Just like when we see a single sentence by itself, a single statement by itself, like California is the most populous state in the United States of America, that sentence was grammatically complete. And that sentence can be represented by a single letter, like C. And because of that, we can say that any single letter by itself is grammatically complete. It is a full statement wrapped up into a single letter. For our purposes, it might often be helpful just to kind of give this a little bit more context while we kind of learn these concepts, that when we do see a single letter, to read it as X is true. So although we would say, if I were to tell you, I grew up in Minnesota, right? You're having a conversation with someone, and they said, yeah, last weekend I saw that the most recent horror film that came out. And then you would think to yourself, what is the truth value for that? What are they telling me the truth value for that statement is? Generally, the answer is going to be true, yeah? Like, if I were to tell you, think about these two sentences. You ask me where I'm from, we're just talking. You ask me where I'm from, and I say, I'm from Minnesota. And then imagine this different scenario where you ask me where I'm from, and I say, it is true that I am from Minnesota. What's the difference between those two statements? There isn't really any one. When somebody just says something, it's taken for granted that they are asserting something is true. I don't have to follow every one of the sentences that I'm saying right now with the statement is true. I had a tuna sandwich for lunch. That is true. I ate oat. It is true that I ate oatmeal for breakfast. Can you imagine if you knew someone who thought that they had to say the truth value of every statement that they uttered? Like, you don't have to do that. We generally will take for granted that when someone says something, when someone asserts something, that they are also asserting it is true until they tell us otherwise. Like, for example, if I said, I ate ice cream, I ate an ice cream cone for lunch, that's false. Like, then I have to say it's false. When somebody asserts something and they want to communicate that that statement that they uttered was false, they got to say that. They got to say something like that was false. But you don't have to say it that it was true. That's just taken for granted. Okay. So what I'm saying here is that when you're reading these statements, sometimes it is useful to read the is true into the statement just to help us sort of like lock down with our minds to understand how to read this kind of like new language that we are going to be looking at. Speaking of food, it's getting close to that time, but we will do this video, take our time with it, and then I will eat. Anyhow, so first up, we're going to have to look at some operators, and we are going to be dealing initially with 4 different operators: and, or, not, and if then. Okay, and, or, not, and if then. There's going to be another one called if and only if, but we will get to that. That's kind of like better understood as a combination of terms, of operators. So we'll just set that aside for the time being. But that means, so I would take out your notebook and write these down: and, or, not, and if then. Okay. These are operators. What do we mean by an operator? Think about arithmetic. There's an analogy to be had here with similar origins. In the statement 5 plus 7, that is what we might call a grammatically correct arithmetics problem. 5 plus 7. 5 has a value, 5. 7 has a value, 7. In other words, 5 is 5 units of 1. 7 is 7 units of 1. That's what those two symbols represent. What is the operator? The operator is the plus symbol. It's the symbol of addition. And what that operator does is tell us how we're supposed to understand the relationship between those two different values. So we take the arithmetic problem 7 plus 5. What is the answer to that? And you know, it's 12. It's 12. And we don't need, because we understand the basics of arithmetic, we understand that 7 plus 5, you take the 7 units of 1, we take the 5 units of 1, and the operator and instructs us, like a computer, to figure out what the equivalent of that is. It's a function. If we change the operator from an and to a or, it's also going to change the logic in propositional logic. Likewise, in arithmetic, if we have 7 plus 5, that gives us 12. But if we have 7 minus 5, in other words, we take away the operator of addition, and we put in the operator of subtraction. We take out the plus, and we put in the minus. That changes what that means. Now, instead of meaning 12, that's going to mean 2. 7 minus 5 equals 2. Now, if you're worried this is getting too much into mathematics, first of all, don't worry about it. Like, maybe that's probably not going to make anyone feel better. But I will say this. This is simpler than arithmetic. And I'll tell you why it's simpler. One, we're never going to get more than these operators. We're going to have and, or, not, if, then, and if and only if. Like this semester, that's it. That's all we're going to do. And there are more complicated ones, but we're not going to do that here. That's like beyond the level, beyond the scope of this class. Another reason why it's easier is because, like, okay, let me slow down and take a breath. I'm excited. In arithmetic, each number's place can have any one of 10 different values, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you have a different numbers place, sometimes in the same number, that represents tens. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, so on, 100, 200, 300, 400, thousands, 2,000. All of those can be in the same number. So we might have, you know, any number can have an infinite number of values. And it's like on these rotating wheels of 10 different symbols. Infinite compared to what do we have in logic here? For us, each symbol can only have 2 values, true and false, okay? Some of you may wonder, that sounds interesting. Is this what binary mathematics is? And if you thought that, you'd be right. Binary mathematics symbolizes all numbers as ones and zeros. And truth or false, or in a light switch, on and off. In logic, true and false, all the same thing. Here, the reason why we use true and false is because what we are trying to work with are statements that refer to something in the world for the sake of analyzing arguments. In binary mathematics, we are generally trying to understand a form of mathematics that can be processed by a computer that can only read ones and zeros. If you do electrical work and are examining an electrical circuit, the switches must be on or off. And sometimes the switches can change their nature, but that's something totally different. But in general, you are concerned with, is this circuit active or is this circuit inactive? And that's everything for you when you're doing that electrical work. But it's the same system, simply appropriated for different purposes in the world, which is why if you have taken discrete mathematics or you have worked in binary stuff, in computer programs, and electrical circuits, or you play the right kind of video games, like this will feel similar. Because it is. Technically, it's not even math. It's like proto-math or something. That's a whole different kind of conversation. Okay, it's math-like for sure. Now, let's look at these. When we say X and Y, when that's our sentence, or in other words, if I were to take my own advice from the previous slide, when we say X is true and Y is true as a single statement. So now we had the single statement. So X is a single statement. Y is a single statement. We can also have the statement X and Y. X is true and Y is true. That would be something like when I say, you know, I was born in Iran and my brother was born in Seattle. Okay, like that's a whole sentence, but it was composed of 2 different statements. One statement by itself is, I was born in Iran. And another statement is, my brother was born in Seattle. But we can put those together into the same sentence, and it just conveys the same meaning, right? This is the and operator. This is our most basic one. The and operator, so when we say X is true and Y is true, we mean that both X is true and Y is true. Like, you're like, duh, obviously. Another way to think about that, and this is going to be important, like I know this is some of this stuff is like so obvious, but the reason why it needs to be obvious and needs to be like taken so completely and plainly is that we need to make sure we have every single detail of these simplest things as like our solid building blocks, so that when we advance and put one piece on top of another, it still makes sense. And I think one thing that students will often do is assume that something was so simple they believed that it made sense. They move forward and then suddenly they're like, I have no idea what's going on anymore. Like, we have to just accept that we are looking at things we already know in a slightly new way so that we can go further than we have before. Let's just talk about that for a second. This is an interruption to the normal programming. This concept that sometimes in order to understand something complex, you need to understand the basics first. In other words, you need to take the stuff that was already simple and that we had taken for granted, and we have to make sure we understand every detail of those simpler statements. It feels like going backward before we can go forward. This is what so much of good thought and analysis and discovery involves. And one of the reasons why that's true, like for every problem that we deal with, whether that's a problem of like a philosophical question, a political question, an engineering problem, a scientific question, the question of like how to write a new kind of book, which, you know, writers are asking all the time. In order to see something new, it's not enough to just be creative. There are so many creative innovators that the ground has already been trod. These questions have already been looked at 1,000 times or more over again. And innovation becomes harder and harder to find. But the way forward often begins by stepping back and looking at things anew, breaking down the current problem into its smaller components, examining each one, and then slowly putting them back together again. It is such a critical lesson in learning how to be a better thinker. And you know, your students, you are in a world right now, and I'm not just talking about like, I'm not talking about the unforgettable year that is 2020. I'm just talking about what it means to be a college student. And what it means to be a college student is that you're writing a lot of essays, right? And I was a college student too, in a way I still am. And, you know, we get these assignments that say, write a 5-page paper. And I was there. You write 2.5 pages and you're like, what else can be said about this? I did it. Like, there's nothing else to be bullshit. Sorry. BS. There's nothing more to be said about it. There's just nothing more that we can see about it. There's always more that can be explored, always more that can be examined. And the problem with most the writing skills of new, fresher college students is that we haven't yet understood that what we are looking for in a 5-page essay is not just saying what you think is true or arguing based on what you already know is true, but rather going back down into the argument, examining the pieces, examining your statements carefully, refining those building blocks, refining your premises, and then being much more careful in how you build them and put them back together again. Once you do that, once you learn how to do this in your essay writing, in your thought, in your speech, the problem won't be, how do I get to 5 pages? The new problem is going to be, how do I stop at 20? And if you are working hard to do this, to examine your thoughts, to examine your writings, and you are cultivating the complexity of your argument, you are cultivating how precise you can speak about things, you will no longer have the problem of how do I say enough. You'll begin to have the problem of how do I make sure I can say everything I need to say and not go over 20 pages or something like that. Like, just as an example, I remember the first time that I had to give a 5-minute speech in high school or middle school or whatever. It was terrifying. And it was a hard thing, you know. So many of us were at this position where you're told, give a 5-minute speech, and you're like, oh boy, I have these things that I just gotta BS for like 5 minutes. I remember this so clearly, and it was hilarious, the kind of BS games that students would sometimes come up with to get to those 5 minutes. Want to know how much I like wrote down and give this speech? Like, now I can just talk about these things. In large part because I spent the time to think about the small components. And the same is true for almost anyone who can speak at length about something. I mean, also, we could probably be more concise in many cases as well. But that's usually not the problem when we're starting out here. Okay, getting back to the operators. We are now returning to the regularly scheduled program. When we say X and Y, we mean both X is true and Y is true. The statement X and Y is true is true if both are true. In other words, suppose I were to tell you X is Y, X is true, and Y is true. You can conclude from that X is true, obviously. You can also conclude that Y is true independently. It's like that thing is saying that both of those things are true. Okay. Next, when we say X or Y, we mean that at least one of them is true. At least one, possibly both. The statement is true if at least one is true. So if I were to tell you X is true or Y is true, do we know X is true? We actually don't. Do we know Y is true? We actually don't know that. All we know from the statement X is true or Y is true is we know that at least one of them is true. But individually, it's undetermined whether either one on its own is true. We just know the truth is somewhere there. If you're wondering, well, what if I also knew that X is not true? Well, now we're getting somewhere. Now, if you combine those two things, X is true or Y is true, and X is not true, then it must be the case that Y is true. That's a logical structure that we will learn more about in chapter 11. When we say not X, we mean that X is false. That's our third operator. This is somewhat similar to the negative sign in mathematics. We mean that X is false when we say not X. The statement not X is true if X is false. Finally, when we say if X is true, then Y is true, we mean that if X is true, then Y must be true. But Y can be true even if X is true. We will say that if X, then Y is false whenever X is true and Y is false, since that would violate the statement. Every other combination, however, will be considered true. So let me see what we have on our next slide. Okay. The if-then statement is often the most puzzling one, but we have talked about this before in this class, so hopefully it won't be so bad. But think about that statement. If X is true, then Y is true. Okay. Again, that doesn't say that X is true. This works very much like the or statement. It doesn't mean that the X is true, and it doesn't mean that the Y is true. What it does mean is that there are a few different possibilities, and there's one impossibility. So for this, I'm going to pull out my little board here, a digital board. I'm going to share this whiteboard. Okay. So if X is true, I need to move this down here. If X is true, then Y is true. Okay. Now, one thing to be clear about, this is not going to be very, very clear. I'm going to try to explain this in a number of different ways. This is not about a causation here. It's not saying that if X is true, it causes Y to be true. What it is saying is that in all cases where X is true, Y is also true. Now, these two things don't have to have anything to do with each other, right? This is just about, it's just about the sometimes accidental features of the truth value. It could represent causation. It could represent some kind of connection between what X and Y are representing. If presidential candidate X gets more electoral votes than presidential candidate Y, then presidential candidate X will be the new nominee for president of the United States. Like, it could have a connection, a causation like that, but not necessarily. I'll give you an example, a weird example of that in a moment here. Okay, so you think about these combinations. I'm going to give you what is called a basic truth table, and we're going to learn more about truth tables in a couple of weeks. Okay, so we have X and we have Y, and we have a few different combinations here to think about. One combination is that X is true and Y is true. Okay, in other words, if X is true, then Y is true. That's true. Assume that's true. We're going to take for granted that's true, as if somebody had told us this sentence. That doesn't tell us that X is true. It doesn't tell us that Y is true. It simply says that if X is true, then Y is true. Okay. If this isn't making sense, go back and listen to the video again. Read chapter 10. It'll come together. You'll have time. Another possibility that we should consider, that X is true and Y is false. Another possibility, X is false and Y is true. And finally, that X is false and Y is false. Now, I said that these are possibilities. Actually, one of them is not. Based on this, if this is true, if X is true, then Y is true. 3 of these are possibilities. One of them is impossible. What do you think it might be? If you'd like to, pause the video right now and work it out. But we can just continue on as well. So one last chance, pause the video, then press play. And now I'm going to move forward. The first one's a possibility. If X is true, then Y is true. That one is most clearly true. Yeah. Here we have the condition that X is true. That forces, if this statement is true, then that should force y to be true, and it is. It's true. Okay. Second one, x is true. This is possibility number 2. X is true. Now the statement says if x is true, then y is true. Well, x is true, therefore y should be true. But it's not. And because it's not, we see that this relationship violates the statement. If it's the case that x is true and y is false, that means this statement is false. Did you get that? If x is true, then y is true. Well, in this case, x was true, but y was false. In other words, this part was true. And if since this part is true, if the whole thing is true, it forces y to be true. Except y isn't true in this case. Therefore, this is impossible. Here, if x is true, then y is true. Well, here x is false. Does that mean y should be false? No. This is one of those things where the condition was met, but that doesn't mean that the condition was not met, but that doesn't mean that the effect is also like not met. It can be true that there are multiple ways for y to be true. So for example, here's a logical relationship. If what's a pet's name? If Sox, name this pet was named after the White Sox. If Sox is a cat, then Sox is a mammal. Well, that's true, right? Because cats are mammals. But I'm here to tell you today that Sox is not a cat. Sox is a dog. So that means this first part is false. But if Sox is a dog, does that mean that he's not a mammal? No, he's still a mammal. In other words, when sometimes the antecedent, the first part of this can be false, that doesn't mean that the second part is forced to be false too. It can still be, the statement can still be true. So it might be false, but here, the way we're going to deal with the if-then statement in logic, which is the same as we do it in discrete mathematics or other systems that use the same format, we're going to treat this as a possibility. If this is true, in other words, here's another way of looking at it. If this is true, and assuming we don't have any other information about the relationship between x and y, then this is a possibility. Okay? It's a possibility that x is false and y is true. Finally, what if x is false and y is false? Is that a possibility? And again, the answer is yes. Remember when I told you that Sox was not a cat and that was in fact a dog? I lied. Sox is a turtle, which means that the first part is false and the second part is false. Sox as a turtle is neither a cat or a mammal. However, it is still true that if Sox was a cat, then Sox would be a mammal. In other words, the statement is still true. In other words, when this statement is true, it's still a possibility that both the first part, the if part, and the then part are both false. Okay. So going back to our slide, but y can be true even if x is true. We will say that if x, then y is false whenever x is true and y is false, since that violates the statement. Every other combination, however, will be considered true. Okay. We're going to leave it. We're going to leave this video at this point. I'm going to come back this week with some examples for us to try out. And then on Wednesday's class, we're going to work on some things in class. Hope you're having a good day. Take it easy. Stay healthy. The pandemic is sparking once again. So I hope you're staying safe. An election day is, as I'm sitting here, a mere 8 days away. Hope you've all had the chance to get out there and vote. If not, please do so. I'm not going to tell you who you should vote for. That's your choice. But to have a strong, functioning democratic society or democratic republic, whatever you want to call it, it's important that we all get out there. Have a good one, and I will see you soon.